Welcome to lecture 16. So, this is the first lecture of week 4 and in this week we will talk about basic concepts of optimization part 2. In week 3 we talked about basic concepts of optimization part 1 where we mostly concentrated on optimality criteria for unconstrained single variable and multivariable functions. In this week under basic concepts in optimization part 2, we will talk about optimality criteria for constrained functions. So, now we will talk about optimization problems with one or more constants. We will start with optimization problems with equality constants and then move on to general nonlinear programming problems where you will have both equality and inequality constraint. So, in this week we plan to talk about equality constant problems. Under equality constant problems, we will talk about different methods or approaches to solve such problems such as variable elimination method, method of constant variation and Lagrange multipliers. Then we will talk about general nonlinear programming problems and as optimality criteria, we will talk about Kuhn-Tucker condition also known as KT conditions. So, today we will start our discussion with equality constant problems and introduction and we will talk about two methods, one is variable elimination method and method of constant variation in today's class. So, let us first try to understand one more time the difference between constrained and unconstrained problems. Unconstrained optimization finds a minimum of a function under the assumption that the decision variables can take on any possible value, but generally additional constants exist that limit the range of feasible values for decision variables. For example, the unconstant function f x equal to x minus 4 whole square if we consider and ask what is the minimum for this function f x equal to x minus 4 whole square. The function is x minus 4 whole square. So, obviously, the minimum possible value is 0 and that happens when x equal to 4. So, the answer is 4. Let us now take the same objective function, but now let us put some constant on x. So, for example, let us consider the objective function f x equal to x minus 4 whole square subject to x is greater or equal to 5. So, x cannot be less than 5, it can be 5 or greater than that. So, what is the solution now? Again obviously, the solution is x equal to 5. At x equal to 5, the function value is 5 minus 4 whole square equal to 1. Any value greater than 5 will give you a greater objective function value than 1. So, the minimum value is 1 under these constants. Note that x equal to 5 is not a stationary point for the unconstant problem. If we consider df dx equal to 2 into x minus 4, if we evaluate it at x equal to 5, it will be 2. Let us consider the function shown on the screen. So, if we consider there is no constraint on the function, what will be the minimum value of the function? So, this is the sketch of the function and if you look at the function, the unconstant minimum happens here. But if I put some constraints on independent variable x, that x varies between 0.5 to 1.5, then you have to find the minimum within this range of x. So, in that case the minimum happens here, because the function value here is less than these points or point anywhere else within the range. Similarly, let us now consider the contour plots as shown. So, this is the contour plot of a two variable function of x and y. So, this is the direction in which the function value increases as shown by the contours. So, we are considering the maximization of this two variable function, and we have this constraint which is shown by this curve. So, since we are trying to find out the maximum, we must move in this direction. But because of the presence of this constraint, I cannot consider this as minimum, but this is the point which is minimum. So, this is how the presence of constraint will restrict the decision variable and influence the minimum or maximum value of the objective function. So, now let us formally define equality constant problems. So, what is the formal problem statement for an equality constant problem? So, consider this expression: minimize f x subject to h I x I equal to 1 to m. So, we are considering n variable function, x belongs to n dimensional real space. So, we are considering a function f x which may be n variable function, and there are m number of equality constants. So, all the constants are of equality type: h 1 x equal to 0, h 2 x equal to 0, h 3 x equal to 0 up to h m x equal to 0. This can also be written compactly as minimization of f x, where we understand that x is n dimensional vector subject to h x equal to 0. Note that m is less or equal to n. If m is greater than n, that means if you have more number of constants, then you have variables, the problem will be overdefined and there will be no solution. The multivariable function f x may be subject to one or more equality constants of many variables. These equality constants may or may not be linear. So, for equality constant problems, we will consider three different types of methods of solution: variable elimination method, method of constant variation, and method of Lagrange multipliers. In this lecture, we will talk about variable elimination method and method of constant variation. So, let us start with variable elimination method. So, we have an equality constant optimization problem: minimize f x, where x is n vector subject to h I x equal to 0, I varies from 1 to m. So, we are minimizing an n variable functions subject to m number of equality constants. An equality constraint optimization problem can in principle be solved by converting it to an unconstant problem by explicitly eliminating m independent variables using the m equality constants. So, idea is as follows: if you have a two variable function x1 and x2, and if you have a constant, let us say single constant, which is a function of x1 and x2, I can make use of this equality constant to express x1 in terms of x2 and then can substitute that in the objective function, so that the objective function will be in terms of x2 alone. You can also do the other way round, like you can express x1 in terms of x2 or x2 in terms of x1, whatever way you like, and can substitute it in the objective function, and the objective function will be now converted to a single variable objective function. It will also be converted to an unconstant problem, because the constants have now been incorporated in the objective function. So, in principle, this can be extended to a problem where you have n number of variables and you have m number of equality constants. So, all these constants can be used to express one variable with respect to others and can be substituted back into the objective function to convert the objective function into an unconstant objective function. So, all the equality constants are basically getting incorporated in the objective function. Then you will have an unconstant objective function, and the optimality conditions that we have talked about for unconstant optimization problems will apply readily. That means, you will take the gradient equal to 0 to find the stationary points, and then you will consider the Hessian to find out local minimum, local maximum or saddle point. This is for multivariable function. If you just have two variable functions and one constant, you will either express x1 in terms of x2 or x2 in terms of x1, and the objective function will be a single variable function. So, the optimality condition for single variable will readily apply. So, df dx will set equal to 0 and take the higher order derivative to conclude whether it is the point of minimum or point of maximum or point of inflection. So, let us now take an example and clarify this. So, we will take an example of two variable, minimize the function 4 x square plus 5 x square plus 10 subject to one equality constant 2 x 1 plus 3 x 2 equal to 6. So, let us look at the objective function. You can readily conclude that the unconstant minimum is x 1 equal to 0 and x 2 equal to 0, because in that case the function value is 0 plus 10 equal to 10. For all other values of x 1 and x 2, the function value will be more than 10. So, this is for unconstrained objective function, but you have a constant 2 x 1 plus 3 x 2 equal to 6. So, x 1 equal to 0, x 2 equal to 0 will not be the optimal solution. So, let us try variable elimination method. We can write x 1 as 6 minus 3 x 2 by 2 from this equality constant. Now, let us put this x 1 into this objective function and get this expression, which is now expression in one variable, and it is also unconstrained because the constant now has been absorbed in the objective function. So, I have now an unconstrained objective function of single variable x 2. So, now the optimality criteria for unconstant problems can be used to find the optimal solution. You can use both necessary and sufficient conditions. If you look at the plot of the objective function, the objective function is the surface of a paraboloid in 3-dimensional space. And 2x1 plus 3x2 equal to 6 is the plane. Now, consider the intersection of the paraboloid and the plane representing the constraint. That means, consider the intersection of the paraboloid and the plane represented by 2x1 plus 3x2 equal to 6. The projection of this intersection onto the plane fx2 equal to x2 plane is a parabola, and we are basically finding out the minimum of this parabola. So, now going back to this, to find out the minimum of this, you have to take df dx2 equal to 0, and the value that you get has to be checked whether it is minimum or maximum, and that you can do by taking second order derivative. If it is greater than 0, the point is minimum. So, by that you will get the value of x 2. Once you get the value of x 2, you can get the value of x 1 from this equation. So, if you solve this, you will get the value of x 2 as 1.285. And x 1 can also then be found out from the constraint 2x1 plus 3x2 equal to 6. Next, let us talk about method of constraint variation. Let us consider a 2 variable function with a single equality constraint. So, we are considering a function f of x 1 and x 2. We want to minimize f of x 1 and x 2 subject to constant h x 1 x 2 equal to 0. So, you have a 2 variable function and a single equality constant. If the function f has a minimum at x star, which is x 1 star and x 2 star, a necessary condition is that the total derivative of f must be 0 at x 1 star and x 2 star. So, if f has a minimum at x star, that is point x 1 star x 2 star, a necessary condition is that the total derivative of f must be 0 at x 1 star x 2 star. That means, df will be equal to del f del x 1 dx 1 plus del f del x 2 dx 2 equal to 0. So, this you get by taking the total derivative of this function. So, the total derivative of the function f is df equal to del f del x 1 dx 1 plus del f del x 2 to dx 2. So, this total derivative must be equal to 0 at x 1 star x 2 star if x 1 star x 2 star is the minimum point. Since h x 1 star x 2 star equal to 0 at the minimum point, any variations dx1 and dx2 about the point x1 star x2 star are admissible variations if the point lies on the constraint. That means, h of x1 star plus dx1, x2 star plus dx2 will be equal to 0. Why? The reason is as follows. We are saying that x1 star x2 star is a minimum. So, if x1 star x2 star is a minimum, it must satisfy this constant h x1 x2 equal to 0. Now, look at the figure. This figure, the PQ curve represents the constant curve. So, the solution will lie on this constant curve. Now, if I consider the point A as x1 star x2 star, any variations along C and along B will be admissible variations. Why? Because the points still lie on the constant curve. That means, the points still satisfy the constant h equal to 0. But any variation along D will violate the constraint and not admissible variations. So, I know x1 star and x2 star satisfies the constraint. So, a small deviation from x1 star x2 star will be admissible variations if these deviations also satisfies the constant h equal to 0. That means, h1 x1 star plus dx1 and x2 star plus dx2 is also equal to 0. So, this is the definition of admissible variations. So, now the Taylor series expansion of the function h x1 star plus dx1, x2 star plus dx2 equal to 0 about x1 star and x2 star will give the expression as shown here. We will simply do Taylor series expansion of h x1 star plus dx1, x2 star plus dx2 equal to 0. So, once we do this Taylor series expansion, why do we get this? And in this expansion, we return only the first order terms, dx1 and dx2 are small. Now, h of x1 star x2 star equal to 0, because x1 star x2 star is a minimum point and that will satisfy the constant h x2 equal to 0. And h x1 star plus dx1, x2 star plus dx2 equal to 0, because admissible variations. If it has to be admissible variations, the condition is written as this. So, del h del x1 dx1 plus del h del x2 dx2 equal to 0 at x1 star x2 star. So, this is the condition that must be satisfied for all admissible variations. If you now assume del h del x1 is not equal to 0, we can write dx2 equal to minus del h del x1 by del h del x2 into dx1. Just rearrange this, considering del h del x2 is not equal to 0. So, considering del h del x2 is not equal to 0, you can write this. Note that considering del h del x1 is not equal to 0, you could have also written a similar expression for dx1. So, idea is the equation indicates that once variation along x1, that is dx1, is chosen arbitrarily, the variation along x2, that is dx2, is decided automatically to satisfy the condition for the admissible variations. So, since the admissible variation must satisfy this condition, if I fix dx1, dx2 is automatically fixed, or if I fix dx2, dx1 is automatically fixed. So, now let us combine the total derivative df, that will be equal to 0 at point of minimum, and the condition that is given by the admissible variations. So, if we combine this, we get this expression for df, which will be equal to 0 at x1 star, x2 star, which are the likely minimum. So, this equation represents constant variation of f, and this must be satisfied for all values of dx1. Now, dx1 is arbitrary, it is a variation. So, it can be made positive, it can be made negative. So, we must have this term equal to 0 at x1 star, x2 star. In other words, this will be equal to 0 and x1 star, x2 star, and this is the necessary condition for x1 star, x2 stars to be an extreme point, that means maximum or minimum. So, this is the condition that must be satisfied if the point x1 star, x2 star has to be an extremum. That means, if it has to be a candidate point for maximum or minimum, this is the condition that must be satisfied according to method of constraint variation. So, let us now take the same example one more time. So, you consider the function 4x1 square plus 5x2 square plus 10 subject to single equality constant 2x1 plus 3x2 equal to 6. This was the condition for x1 star, x2 stars to be an extreme point. So, let us now evaluate del f del x1, del f del x2, del h del x1 and del h del x2. If we put all these values for the partial derivatives, I get this, which can be solved for x1, and x1 can be expressed as 5x2 by 6. So, x1 is expressed in terms of x2 using the necessary condition that we obtained. So, now I can make use of the equality constant 2x1 plus 6x2 equal to 6 and can replace x1 equal to 5x2 by 6. So, I get x2 star equal to 1.285. You remember, we also mentioned that you will get x2 star equal to 1.285 if you use method of variable elimination. Once you have got x2 star, x1 star can be found out by 5x2 by 6, which is 1.071. If you apply the variable elimination method, you will get the same answer. So, with this we will stop lecture 16.